All right, we are going to start Chapter 10, Gases. Now, the good thing about Chapter 10 is it's really not a whole lot of new information from what we learned last year when we were talking about gases. We covered most of this information when we talked about gases last year. We're just going to expand on bits and pieces. In section 10.1, though, it's really just reviewing what we learned last year and adding just a handful of things to the equations. So gases, let's review a couple common things about gases. Unlike solids and liquids, gases expand to fill their container. So right now the amount of air in the room is filling the air in the room. I could compress that air down into a can. I also, if I blew the roof off the school, the air would expand to fit the size of the earth or whatever was left once I blew the roof off. Gases are highly compressible and they have extremely low densities. When we talk about gases, we're going to focus on pressure. Pressure is one of the three key things that we can talk about with a gas. And pressure, remember, is equal to force divided by area. Force is measured in the newtons. Area is typically measured in meters squared. However, it can be measured in other metric units. And atmospheric pressure is the weight of air per unit of area. Now, we didn't really talk about this, but the weight of air on your body is 14.7 pounds per square inch. So if you drew a square inch on the surface of your hand, there's 14.7 pounds of atmospheric pressure pushing down on just that one square inch. So imagine how much is pushing down on your body. The air actually weighs quite a bit. There's quite a bit of pressure created by the atmosphere on you. When we talk about units of pressure, there are a handful of units of pressure that we're going to talk about. There are pascals, which is more of a physics unit. There are bars. Right? There are kilopascals, which are just kPa. And then we have atmospheres, torr, and millimeters of mercury. And all of these are interchangeable. So just kind of keep in mind, we particularly like using atmospheres in chemistry. So 1 atmosphere is equal to 101.3 kPa, which is equal to 760 torr, which is equal to 760 millimeters mercury. Now, bars, we don't really use bars too much. Millibars, that's more of a meteorological unit than anything else. But refreshing that those 4 units, kilopascals, atmospheres, torrs, millimeters of mercury, and then just regular pascals, are very common units of pressure. This slide it's talking about the extension of torr. You don't need to know that. So standard pressure, normal atmospheric pressure at sea level is referred to as standard pressure. That's referred to as 1 atmosphere, or 760 torr, or 101.325 kPa, or 101,325 pascals. What we're going to do with pressure is we're going to focus on studying the key equations that we can talk about when we have pressure. And Boyle's law, remember, is one that we talked about last year. P1V1 is equal to P2V2, which means that temperature, the volume is inversely proportional to pressure when the temperature is held constant. So in Boyle's law, we're assuming the pressure is held constant. So P1 V1 is equal to P2 V2. Just kind of refreshing our equations. Now, what they'll do is expanding upon that equation. If you're going to graph volume and pressure, a plot of volume and pressure is going to be a straight line. So showing that P and V are inversely proportional. So if you graph V to 1 over P or P to 1 over V, they'll have a straight line just to show that they are proportional. Next up, one that we talked about last year as well is Charles' law. Now instead of worrying about pressure, Charles' law is going to worry about volume and temperature. V1 over T1 is equal to V2 over T2. just showing how volume and temperature are related. Remember, there are really four ways we can study a gas: through pressure, through volume, through temperature, and then through the number of moles that exists in that gas. And again, same thing here, showing that they're proportional to one another. A plot of V versus T would be a straight line of any gas. So that's just Charles' law. Avogadro's law. Remember, I just mentioned we are talking about you can measure with pressure, volume, temperature, and moles. Avogadro's law is going to mathematically throw in the number of moles. So if we talk about the number of moles of any gas at STP, remember STP is 0 degrees Celsius or 273 Kelvin in 1 atmosphere. At STP, 1 mole of any gas takes up 22.4 liters. So just kind of keep that in mind. At a constant, at STP, 1 mole takes up 24.2 liters. Now, what we can do is to get an ideal gas equation, we can combine Boyle's law, Charles' law, and Avogadro's law with the idea of moles, and we can get PV is equal to nRT, where P is pressure, V is volume, N is the number of moles, R is our gas constant, which we'll talk about in a second, and T is our temperature. And remember, when we're talking about gases, T is most likely our temperature in Kelvin. So we have to start working in Kelvin when we're talking about gas laws. Now, I mentioned on the last slide R. R can change. How can R change if it's a constant? Because you can have varying units for pressure, volume, and temperature. If those units change, your unit for R is going to change. So I might take a snippet of this slide right here and kind of file that away. Because what's going to happen is we're going to continue to use R throughout the year. But what's going to happen is that we sometimes will use joules, and then sometimes we'll use liters and atmospheres. Now, there's a big difference between the two. Your R values are going to change. So keep that in mind. I would take a picture of this slide and I would save it because your R values are always going to change based upon your units. Sometimes we're in joules if we're talking energy, and sometimes we're in liters and atmospheres. And that R value will change dependent upon that. So keep that in mind. Now, the ideal gas equation, they just rearrange it to show you that PV equals nRT. Nothing new there. However, here's the cool thing using PV equals nRT. We can figure out the density of any gas. Now, the equation for density is what? Mass divided by volume. Correct? Well, N divided by V is equal to P divided by RT. However, if we wanted to get moles to mass, we're going to multiply it by the molecular mass. So what we have here is density of a gas is equal to mass divided by volume, or it's equal to pressure times the molecular mass of the gas divided by R times T. So by rearranging the ideal gas equation, we can help solve for the density of a gas. Just like that. All we need to know to solve for the density of the gas is its molecular mass. So if you wanted to rearrange it, you could figure out the molecular mass of a gas is equal to its density times R times T divided by P. All we're doing there is we're rearranging the equation simply to solve for the molecular mass of a gas over the density of a gas. Last couple things here. Dalton's partial pressures. Let's say I had 3 gases in a container. The total pressure of the gas was 1,000 atmospheres. And the 3 gases were oxygen, carbon dioxide, and helium. Helium took up 500 atmospheres. Carbon dioxide took up 200 atmospheres. How many atmospheres would that oxygen take up? I had 1,000 atmospheres total. 500 atmospheres were taken up by carbon dioxide. 200 atmospheres were taken up by helium. How much is taken up by oxygen? All you're going to do to figure out the total pressures is add all the pressures of each gas together. So in that example, the total pressure was 1,000. Gas 1, which was oxygen, was 500. Gas 2, which is helium, was 200. Figure out for gas 3, and it ends up being 300. All right, just a simple thing there. So partial pressures, that's kind of sums up partial pressures. So that is just a review of all our basic equations. We're talking about Boyle's law. P1 V1 is equal to P2 V2. We're talking about Charles' law. V1 over T1 is equal to V2 over T2. We're talking to the ideal gas law, PV equals nRT. Using that ideal gas law, we can solve for density, and then we talked about the partial pressures law. So all of those are laws and equations that we can use to help calculate variables about a gas.